When you prompt a chat interface, the response feels like a software achievement, the output of an elegant transformer architecture running on a remote server. The physical reality is more complex. Training a GPT-4 class model is a specialized operation that requires thousands of GPUs running in a coordinated cluster for months. It is a sustained battle against computational physics. At a scale of hundreds of billions of parameters, the model generates a volume of intermediate data that exceeds the memory of any individual GPU. A modern H100 or A100 is capped at 80 gigabytes. The math of the model simply does not fit on the silicon. This diagram shows the engineering pipeline required to navigate those limits. It moves through stages: architecture design, data foundations, distributed training, alignment, and inference. Scaling a model to this level is a triumph of system engineering. It requires solving for memory sharding, network latency, and power constraints, rather than simply adjusting mathematical equations. The engineering shift began with the architecture. While the original transformer used an encoder-decoder structure for translation, modern LLMs are almost exclusively decoder-only. Causal masking blacks out the matrice's upper triangle, preventing the model from seeing future tokens. It predicts the next token using only prior context. To maintain order, relative positional encoding dynamically calculates distance between data points, allowing much longer sequences. This architecture is the engine, but it requires massive amounts of fuel. Training a model with 100 billion parameters requires trillions of tokens sourced from across the internet. Raw web data is messy and repetitive. Pre-processing uses heuristic filters, deduplication to prevent over-indexing, and privacy scrubbing for sensitive data. Some models, like Llama 2, take a different approach. They retain more raw data during pre-training to maximize the model's ability to generalize, relying on later alignment stages to handle safety and toxicity. If the raw data pipeline isn't engineered to filter out noise at the start, no amount of architectural tuning can fix the resulting model. Even with perfect data, the hardware presents a hard limit. A modern 175 billion parameter model requires over 350 gigabytes of memory just to load its weights. The standard solution is data parallelism. The dataset is split into batches, and the entire model is replicated across multiple GPUs so they can process those batches at the same time. However, data parallelism creates a massive redundancy. Every GPU in the cluster is wasting VRAM by holding the exact same set of parameters and optimizer states. In an all-reduce operation, nodes pool gradient calculations into a single aggregate, broadcasted back to update weights. To solve redundancy, model parallelism slices large linear layer matrices into fragments, distributing them across GPUs to work on mathematical operations in pieces. When horizontal scaling hits its limit, engineers must break the model's parameters apart and distribute them across the physical hardware of the server rack. For models scaling toward 200 billion parameters and beyond, developers use the Zero Redundancy Optimizer, or ZERO. Zero Stage 1 shards optimizer states, spreading them across the cluster. Stage 2 shards gradients, freeing VRAM during backpropagation. Stage 3 shards model parameters. Fragments assembled just in time for calculation, then immediately release back to their host GPUs. Pipeline parallelism adds a vertical layer to this. It slices the transformer layer by layer across physical machines, passing data from layer 1 on GPU A to layer 2 on GPU B. Further efficiency comes from mixed precision training, which uses 16-bit math for speed and 32-bit for accuracy, and checkpoint recomputation, which deletes intermediate results and recalculates them only when needed for backward passes. Zero is a calculated trade-off. It increases the volume of communication across the network to save the GPU memory space required to keep the model running. A pre-trained model is essentially a massive pattern matcher. To make it useful, it undergoes supervised fine-tuning, or SFT, trained on instruction and response pairs to learn how to follow prompts. SFT alone doesn't prevent hallucinations or bias. The model still lacks a framework for human values or factual accuracy. Developers align the model to the 3H standard, making it helpful, honest, and harmless. This process is called RLHF. A reward model is trained on human feedback to score responses. A PPO algorithm then uses those scores to continuously adjust the main model's weights. For those with limited hardware, parameter-efficient tuning, like LoRa, freezes the main network and only trains tiny secondary matrices. This allows developers to adapt a model to a new task without the massive cost of a full fine-tune. This alignment stage is what turns raw statistical probability into a safe, commercially viable product. When running the model for users, the inference phase, we encounter a conflict in hardware architecture. The GPU can calculate answers very quickly, but it is limited by how fast it can access the model's weights in memory. Every token generated requires a lookup in the KV cache. As the conversation gets longer, this continuous memory access creates fragmentation and slows down the response time. We solve this physical limit through structural optimizations like page detention and flash attention. Flash attention chunks attention matrices, forcing computation inside the processor's hyper-fast SRAM chip, entirely bypassing the slow, high-bandwidth memory bottleneck. Finally, model compression techniques like knowledge distillation and quantization allow us to shrink the model's footprint, making it possible to run these large networks on consumer-grade hardware. Inference efficiency is the final bottleneck. A model's intelligence is only as useful as its cost to compute for a single user question. This gear system illustrates the unified pipeline. Pre-training data provides the foundation, Zero handles the hardware load, RLHF aligns the behavior, and flash attention manages the deployment speed. We interact with this system through prompt engineering and chain of thought, using specific structures to extract logic from the weights. The field is already moving toward multimodal processing and new architectures like RWKV, which attempt to solve the memory scaling issues inherent in transformers. For developers, understanding the end-to-end hardware and software pipeline is now a baseline requirement for building the next generation of AI tools. 想了解更多关于大模型底层的硬核知识，掌握前沿 AI 技术，邀请大家关注我的频道 Learn by Doing with Steven、数能生智、Steven Data Talk、Steven 数据漫谈等。相关硬核内容在小红书、微信公众号、YouTube、Spotify 等平台同步更新。视频描述和 Show Note 区域有我的 Linktree， 包含所有社交媒体平台的链接。